Hi students, in this chapter we're going to study about what happens when a dielectric is inserted between capacitor plates. You see, some special charges get induced on the dielectric, and these charges even create a reverse electric field inside the dielectric. We are going to study about all this charge that gets induced on the surface of a dielectric when it is inserted between two capacitor plates. So, shall we proceed? Now the first thing we'll study in this chapter is electric polarization. We had already studied about electric polarization a long time ago when we were studying what an electric field is and the effect of electric field on ordinary bodies. But let's revise that. You see, whenever there's a uniform electric field like the one shown on the screen and a dielectric is placed in that electric field, polarization takes place. What happens is that the left part of the dielectric here is definitely at a greater potential compared to the right part of the dielectric, isn't it? That is obvious because electric field lines always move from a place of higher potential to a place at a lower potential. So basically, this place is more positive than this place. Now because of this polarity, the electrons inside the dielectric get attractive towards the more positive portion of the dielectric. And similarly, positive charges are created at this place of lower potential. Now this creation of negative charges and positive charges in the dielectric is termed polarization. Now because of this creation of negative and positive charges, an electric field called EP, or the electric field due to polarization, starts acting inside the dielectric from right to left, that is, from the positive charge towards the negative charge, and therefore the net electric field inside a dielectric is actually E external minus E polarization. Understood? So outside the dielectric, the electric field is simply E external or E. However, inside the dielectric, since this electric field is also countered by the polarization electric field, the net internal electric field in a dielectric is E external minus E polarization. Understood? So this phenomenon of polarization in a dielectric is something you need to understand for competitive examinations. Now, if E internal is E external minus E polarization, what will happen, if this E here is actually the electric field because of a capacitor? What if you add two capacitor plates like this and make sure that the electric field in this region is because of the capacitor plates? Well, in that case, you can clearly represent E external by sigma by epsilon naught, because we already know that the electric field between two capacitor plates is sigma by epsilon naught. In that case, the electric field inside the dielectric is sigma by epsilon naught by K. This is because we had studied in the chapter related to electric field that the electric field inside a dielectric, I'll call it E internal, is always equal to E external, or the electric field outside the dielectric, divided by K, where K is the dielectric constant of the dielectric. In fact, K is the ratio of the external electric field to the internal electric field. Now in this case, since the external electric field is sigma by epsilon naught, the internal electric field inside the dielectric will be sigma by epsilon naught divided by K. And therefore, E polarization can be represented as sigma dash by epsilon naught. Sigma dash here represents the induced charge density on the dielectric, just as sigma represents the charge density on the capacitor plates. We can calculate the value of sigma dash by using this equation. Our aim in learning about all these induced charges and polarization is to basically calculate the net induced charge density on the dielectric surfaces, or the net induced charges on the dielectric surfaces. Now since sigma dash represents the induced charge density, on simplification we get this expression: sigma by epsilon naught is K into sigma by epsilon naught minus sigma dash by epsilon naught. When we further simplify this expression, we get sigma dash as sigma into 1 minus 1 by K. Now this is a very important expression and you have to remember it. What this expression says is that the induced charge density on the surface of a dielectric is equal to the charge density on the plates of the capacitor into 1 minus 1 by k, where k is the dielectric constants of the dielectric. Understood? Now sigma is simply q by a. So if we replace sigma dash by q dash by a and sigma by q by a, we get q dash equal to q into 1 minus 1 by k. Again, this implies that the net induced charges on the surface of a dielectric are 1 minus 1 by k times the net charge on the capacitor plates. So essentially, in this derivation, what we really did was we tried to calculate the electric field inside a dielectric. The electric field inside a dielectric will clearly be the electric field outside the dielectric minus the polarization electric field, isn't it? Then we substituted expressions for the electric field inside the dielectric, which is E external divided by K. We substituted the expression for E polarization as sigma dash by epsilon naught, and we substituted the expression for the external electric field as sigma by epsilon naught. That gave us our final answer. So this was about the induced charges on the surface of a dielectric. Let's now move on to the next concept in this chapter. The next concept relates to what happens to a capacitor when a dielectric slab is inserted in it. Like what happens to the properties of the capacitor? How does the potential difference across it change? How does the charge on a capacitor change? How does its capacitance change? How does the energy stored in a capacitor change? When a dielectric slab is inserted in it? That's the concept we're going to study right now. So as you can see, there's this capacitor which has charge plus Q and minus Q on its plates. This capacitor is connected to a battery with a potential difference V. Now, keeping the battery connected, we insert a dielectric inside this capacitor. When we do that, the charge on the capacitor becomes Q dash and minus Q dash. So let's have a look at exactly what happens to each property of the capacitor. What happens to the potential difference across the capacitor plates? Well, the potential difference has to remain constant. This is because the battery is still connected to the capacitor plates, and the potential difference across the battery has to be the same as the potential difference across the capacitor plates. So V is constant irrespective of the introduction of the dielectric slab. What happens to the capacitance of the capacitor? We already know that when we insert a dielectric in a capacitor, the capacitance gets multiplied by K. So basically C dash is K times C. Now what happens to the charge stored on the capacitor? The charge stored also gets multiplied by K. This is because the charge stored is capacitance into the potential difference of the capacitor. Now the capacitance is K times C and the potential difference is the same, it's V. So Q dash is K into C into V, that is K times the initial charge stored. So you must remember that when a battery is connected to a capacitor, the charge gets multiplied by K. When a dielectric of dielectric constant K is introduced into the capacitor. What about the energy stored in the capacitor? Any guesses? Well, clearly, the energy is half into capacitance into V square. V is constant and C gets multiplied by K. So clearly, the net energy stored in the capacitor becomes K times the initial energy, half into KCV square instead of half into CV square. So those were the properties of the capacitor, when a dielectric slab was inserted in it, but we had kept the battery connected. What would have happened, had we not kept this battery connected? Had we removed the battery and then inserted the dielectric slab? Well, let's try it right away. Here, the battery has been disconnected and the capacitor has a charge plus Q and minus Q on its plates. Now we have inserted a dielectric in between the capacitor plates. First of all, remember, in this case, unlike in the case when the battery was connected, the charge on the capacitor plates will be constant. This is because there is no place for the charges to escape. Where will the charges go? There's no battery, to provide charge or take charge from the capacitor plates. So the charge will be constant. The capacitance again will increase by a factor K. That's because that's the property of a dielectric. It always increases the capacitance by a multiple K no matter what. So C dash is Kc. Now what happens to the potential difference across the capacitor plates? The potential difference across the capacitor plates is not constant this time. This is because there is no battery connected, to supply charge to the capacitor or to take charge away from the capacitor. The potential difference is Q divided by C dash. Now Q is still constant, but C dash is K times C. So the net potential difference across the capacitor plates becomes 1 by K times the initial potential difference. And what about the energy stored in the capacitor? Well, as you already know, the energy stored is Q squared by 2C. Now Q is constant, but C has become K times. So the energy also becomes 1 by K times the initial energy. Note that in the previous case, when a battery was connected to the capacitor, we calculated the energy, by using the formula half CV square. In this case, we are calculating the energy using the formula Q squared by 2C. We are doing that because, in the earlier case, V, the potential was constant. In this case, Q, the charge is constant. So it's easier to calculate the energy using the formula Q squared by 2C when there is no battery. But it's easier to calculate the energy using the formula half CV square when there is a battery. Understood? So all these were small little concepts that could prove to be gems when you go and solve objective type questions. In fact, let's solve a question right away. This question was asked in IIT JEE 1985. A parallel plate air capacitor is connected to a battery. The quantities charge, voltage, electric field and energy associated with this capacitor are given by Q0, V0, E0 and U0 respectively. A dielectric slab is now introduced to fill the space between the plates with the battery still in connection. The corresponding quantities now given by Q, V, E and U are related to the previous ones as Q greater than Q0, V greater than V0, E greater than E0 or U greater than U0. We have to take the correct option. So basically, in this question, we are given a setup very similar to the one that we just discussed. We are given a capacitor. This capacitor has a charge Q0 on its plates. It has an energy U0. It has a field E0 between its plates. And it has a potential difference V0 across its plates. We have to calculate the change in all these quantities when a dielectric slab is introduced between the plates of the capacitor. Isn't that almost exactly the same as what we discussed? Well, let's try to find the answer to this question then. So here, a dielectric slab has been introduced between these two plates. The charge has now become plus Q and minus Q. The energy is U and the electric field is E. The potential difference, however, stays V0 because the battery is still connected. Clearly, V0 remains the same. The charge is C into V0, isn't it? But we know that the capacitance has now become K times C0, the initial capacitance, and the charge has therefore now become K times C0 V0, which is greater than Q0. This is because the charge earlier was C0 V0 and now the charge has become K times C0 V0, which is definitely greater than C0 V0. Hence the new charge Q is definitely greater than the earlier charge Q0. What about the energy stored in the capacitor? Well, the energy stored will clearly be half CV0 square. But C, the new capacitance, is K times C0. So the new energy stored will be half into K into C0 V0 square. Now that is definitely greater than half into C0 V0 square, the initial energy. So U, the new energy, is definitely greater than the initial energy U0. What happens to the electric field? The electric field is clearly V by D. Potential difference remains the same, isn't it? And since the electric field is V by D, the electric field remains exactly the same because the potential difference across the two capacitor plates is the same. Therefore, we can say that E is equal to E naught. V is V naught. U is greater than U naught and Q is greater than Q naught. When we write all these expressions, we can carefully tick our options. Only option number A and option number D are correct. That's because Q is greater than Q naught, U is greater than U naught, but V is equal to V naught and E is equal to E naught when a battery is connected across the capacitor plates. Understood? So that was such a simple IIT JEE problem based on the core concepts that we just discussed.